Hello everybody and welcome to today's video. Today's topic is probably one of the more difficult ones we'll cover in calculus, and that is the chain rule. The chain rule itself is not that complicated, but once you integrate it with other derivative rules, you realize just how complex things get. So first we're going to talk about what the chain rule is, and then we're going to learn how to apply the chain rule in different scenarios. So let's get started on that. So in advanced functions, we learned about composite functions such as f of x is equals to g of h of x, right? This was chapter 8.3. If you don't remember it, you could watch the video I made on it. So now that we know how to derive or differentiate different functions, of course we need to learn how to differentiate these types of functions as well. And in order to do this, we have to learn the chain rule. So the chain rule itself is this. If we have a composite function f of x, then the derivative of f of x is equals to the derivative of g of h of x multiplied by the derivative of h of x. So what this would mean is that you find the derivative of the outer function, so g, right? And then you find the derivative of the inner function, so h, and then you multiply the two. Sometimes it's more useful to use the alternate form of the chain rule, which would be the second notation that we learned about. In that case, we actually have these two friends. So the first one is we say that y is equals to f of u, while u is equals to a function. So this over here is essentially this, right? However, with these two terms, we can actually rewrite the chain rule as simply the derivative of u and the derivative of y, right? So the derivative of y and the derivative of u. So for example, if you were given these two equations, so y is equals to u squared plus 3u, and u is equals to the square root of x, we are asked to determine the derivative at x is equals to 4. So since we're giving this notation, we can apply this format right here. So in this case, what is the derivative of y? Well, the derivative of y would be 2u plus 3, right? Because it's the power rule, so you put 2 on this side, and then this is a constant times a variable, so the variable disappears and we have a 3. Similarly, for the derivative of u, we have the square root of x. The square root of x is the same as x to the power of 1/2, and so we take that half and put in the front, and then we do 0.5 minus 1, and we get negative 0.5. Now combining these two in the format that we have here, right, we actually get the product of 2u plus 3 times 0.5x times negative 0.5. I've immediately plugged in the value of u into our derivative of y, and so we get 2 times the square root of x, because u is the square root of x, plus 3, and then over here I just rewrote what the derivative of u is. So again, this would be 1/2, and then we know that x to the power of negatives would be 1 over the value. So we have x on the bottom, and then to the power of 0.5 is the same as the square root, and so we get 1 divided by 2 times the square root of x. So now all we have to do is simplify. We both have 2 square root of x on both sides, right? So we can extract it, and that would get us the following. Similarly, now that we know what our derivative is, we can plug in 4, and so we get 1 plus 3 divided by 2 square root of 4. The square root of 4 is 2, so you have 2 times 2, which is 4. 3 divided by 4 is 0.75. 1 plus 0.75 is 1.75, and so we got our answer. This right here is actually a special case. And a special case is actually when the outer function is itself a power function. So over here, when we saw that it is, for example, the square root, that's the power, right? That's the power of 0.5. We can apply this notation here. So we say that y is of course the power, then u is still a function. So then the derivative of the power, we know what that is using the power law. So that's n times u, and then u is to the power of n minus 1. And we multiply that by the derivative of u. If we are given what g of x is actually equals to, then we could write it this way. N times g of x, which was our u, to the power of n minus 1 times g prime of x. Again, this might be a little bit complicated for now, but we're going to do a couple of examples which hopefully gets you going on these types of questions. So, for the applications of the chain rule, we have to discuss different scenarios where we have to apply the chain rule. The first one would be, of course, when you have to combine different differentiation rules, such as the product rule with the chain rule. So here is our first example. I immediately chose the really difficult questions for us to do so that we could get practice doing the hard things rather than the extremely easy ones, because you'll always have time to do the easy ones if you're doing the hard ones. So here we're given the curve that is defined by this. We have the fifth root of two variables with exponents on them, and that is all inversed. And then we need to find the equation of the tangent at x is equals to 2. So immediately, I'd recommend rewriting the equation. When you see 1 divided by something, that just means we were given the power of a negative number. And so we get negative here. We also see the fifth root of everything in the denominator, which would mean that we're actually having the power of 1 over 5. And so our actual equation could be written as y is equals to 5x cubed minus 2x squared to the power of negative 1 over 5. So since we're given y, it'd be better to use this notation here as opposed to this notation here, since we're not technically talking about functions, or we're not given function notation here. So in that case, let's call y as the power, right? So y is equals to u to the power of negative 1 over 5. And the inner function would then have to be everything that's in the brackets, which is 5x cubed minus 2x squared. So now we can actually use this definition over here, right? Since we're given a special case where u is to the power of n, and n in our case is the power of negative 1 over 5. So here, let's find the derivative of u. Well, the derivative of u is clearly negative 1.5, we just drag it over here. And then negative 1.5, or sorry, negative 1 over 5 minus 1 is negative 6 over 5. Similarly, we could find the derivative of u, which would be 15x squared minus 4x. Again, just using the power rule, 3 times 5 is 15, 3 minus 1 is 2. 2 times 2 is 4, 2 minus 1 is 1, and so we don't have to write it. Now, we just need to multiply the two together. And so we get this equation here. So we can actually simplify this equation here to this expression. So all I did was I realized that there's a negative exponent, which would mean it's the inverse of this part here, which would mean we have 5x cubed minus 2x squared as our denominator. We also had 1 divided by 5, which would mean this would be the numerator and this would be the denominator. And so that is what I put there. We have 5 from here times this expression here to the power of 6 over 5. The only thing that's left is the negative 1 and this expression, and so we get negative 15x squared minus 4x. Now, using either this form or that form, I substitute x is equals to 2, because that's what the question asked us to find, right? We need to find the tangent. And getting the first derivative would let us have the slope. So I'll plug those values into here, and we get negative 13 over 80, and so our slope is negative 13 over 80. Now that we know what the slope is, we can find the b value, right? Because we're given that x is equals to 2, and we could simply find y by plugging in 2 into our original equation and solving for y, and y turns out to be 0.5. Now, back to grade 9 math, we have y is equals to mx plus b. Plugging in the values, we get 0.5 is equals to negative 13 over 80 times 2 plus b. Isolating everything and putting this to that side, we actually find out that b is equals to 33 over 40, and so the tangent is actually equals to negative 13 over 80x plus 33 over 40. So again, just to go over what we did, we simply rewrote this equation so that it had a power at the top. Then we applied the chain rule for special cases, which was done over here. We found the derivative of each of the appropriate parts. Then we just plugged in 2, found the slope, found a y value, our x value was given, solved for b, and then we got our equation. This question over here is the most difficult one you'll probably do, except for example like thinking questions depending on the teacher you have, but this equation and this derivative will require a lot of effort. So let's see what the question actually is. So like always, new derivative rules allow us to solve more problems revolving around rates of change. Because again, if you find the derivative of, for example, something's position, you could find its velocity, which is exactly what we have here. So we have a particle, a particle's position function, so again just a position time graph, and that is given by this equation here. Ignore the second by. So we know that s is in meters and t is in seconds, and we need to determine the velocity of the particle at 5 seconds. So we're asked for the velocity at a point, which would mean instantaneous velocity, so that would give us this equation here. So v of t is equals to s prime of t. To get f of t, which would be our first part of the equation, I just assigned f of t to that. And then g of t would be the second part of the equation, which would be 1 divided by the square root of 2t minus 1. So this right here would be the product rule, right? Since we're given an equation, times that equation gives us our original function. And what do we know about the product rule? Well, we know the formula. So we need to find f prime of t, and we need to find g prime of t. So how do we do that? F prime of t is really easy. This is just 2 minus t minus 2 to the power of 2. Again, just the power rule, bring 2 to that side, this becomes 1, and so we get 2 times t minus 2. This is a lot of t's. For g prime of t, we actually have to do a lot more effort. So again, this right here could be rewritten because we know 1 and the square root is the same as negative 1 over 2. So now let's apply the formula for the special case of the chain rule. Again, we're given a power and we're given an inner function. So what's the derivative of the outer function? So that would be, for example, u to the power of 1 over 2. Well, we could just use the power rule. So using that, we put negative 1 over 2 in the front. Then we subtract negative 1 from the exponent. So negative 1 over 2 minus 1 is the same as negative 3 over 2. And now we just substitute our inner function back in, and so we get 2t minus 1. The second part of the chain rule is to find the derivative of the inner function, which is 2t minus 1, of course. The constant just disappears, right? But 2t actually turns out to be 2, and so we have the times 2 at the end. Since we have negative 1 over 2 and 2, we can actually group them together, and so we get negative 2t minus 1 to the power of 3 over 2, or negative 3 over 2. Now we have all of the parts we need to plug them into this equation right here. So here they are all plugged in. So we get 2 times 2 minus t minus 2 times 2t minus 1 to the power of negative 1 over 2 plus negative 2t minus 1 to the power of negative 3 over 2 multiplied by 2t minus 2 to the power of 2. This should be a tongue twister. Honestly, if you could say this fast, I'll have to get you like a gold medal. But I don't think anybody could do that. But now that we're given this, we can either substitute t in, right? Because that's what we need to find. Or like most teachers do, you have to actually simplify the equation. Sadly, in high school, your teachers don't want you to take the easy way out, and they want you to get the most simple and the most refined answer you could possibly get. And so we have to simplify the equation. So immediately, let's rewrite it in fraction form. So at first, we're given negative 1 over 2, which we know is just the inverse, right? So that would be 1 over 2t minus 1 to the power of 1/2, which is what we get over here. And these two values stay in the numerator. Similarly, we could do the same thing on this side, and so we get 2t minus 1 to the power of 3 over 2 as our denominator. Now this is where your basic fraction knowledge has to come in. We know to combine two fractions, we need to find the greatest common denominator, right? Or the least common multiple. So what we need to do here is to actually find two numbers that would let us combine 2t minus 1 to the power of 1/2 and 2t minus 1 and 3 over 2. You could do this in two different ways. So in our case, that value would actually be 2t minus 1 to the power of 3 over 2. In case you're wondering why this is, remember that this is the square root of this function or this equation, and this is the third root of this expression to the power of 2. So this right here is much more complicated, but luckily for us, it has the same type of procedure. It's just the roots, right? So we can actually combine them using that. The other way you could have done this is, of course, cross multiply. So you would put 2t minus 1 to the power of 3 over 2 on this side, and then 2t minus 1 to the power of 1 over 2 on this side, and then eventually you'll have to collect like terms and they would cancel each other out or actually simplify to a different answer. But either way should work fine. Here I chose the 3 over 2 one because it's much less work. So knowing that I need to get to 3 over 2, the simplest way to do that would simply be by multiplying this term by 2t minus 1 to the power of 1, right? Because to get to these to this exponent, we need to add 1 to it. Now how do we add 1 to an exponent? Well, we need to multiply its parent base, right, which is 2t minus 1. So that is what I did in this step here. So now we have 2t minus 1 on the top. Here we don't have to change anything because we already have the optimal base. But now that our whole equation has 3 over 2 as the power, we can combine the numerators. And this is what we get. Now comes the easy part, and we just need to open the brackets. So what is 2 times 2 times t minus 2? Well, that's 2t minus 4. And then we know that t minus 2 to the power of 2 would be t squared minus 4t plus 4. But since we have a negative sign, everything gets flipped. And so we get t squared plus 4t minus 4. For our last step, we open these two brackets and we get 4t squared minus 2t minus 8t plus 4, and then we just copy this down. Now let's collect like terms. 4t squared minus t squared is 3t squared, right? Then we have negative 2t minus 8t, which gives us negative 10t and then plus 4t gives us the -6. Then we have a plus 4 and -4, which cancels out, and so we get our final answer, which is 3t squared minus 6t, 2t minus 1, 3 to the power of 3 over 2 as our exponent. The last step that we could do is actually remove the t from the numerator, which is right here, and so we get 3t times t minus 2, and all of it is divided by 2t minus 1 to the power of 3 over 2. Again, going back to the question, we were asked to find the velocity at 5 seconds. So we plug in 5 to our equation, which gives us 5 over 3 meters per second. Again, if you don't have to simplify anything, you could have just plugged it in right here, and you could have gotten the exact same answer. But since teachers do want you to be super careful and want extra things to mark, they're probably going to ask you to simplify your equations. Similarly, if you were given a question where you just had to find the derivative, they would want you to simplify it. You would not be allowed to keep it in this format. So you need to understand these steps we took to get to this answer over here. Again, this is just a recap saying that if you wanted to plug in 5 in the start, you could have, but again, simplifying is probably going to be the biggest thing you have to do in this chapter. With that being said, this is it for today. So of course, here is the homework in case you want some extra practice, which I heavily recommend. The chain rule is, again, arguably the most difficult thing you will learn in calculus and vectors, and knowing how to use it well and doing it quick will be such a big benefit on every test, quiz, and or exam you will do. So doing these 5 questions are bound to help you understand the chain rule better, but hopefully my little examples also helped. Again, thank you so much everybody for listening to today's lesson. I hope you learned a lot, and I can't wait to see you next time. Bye bye!